Hi viewers, welcome to all. Here we are discussing about your project and efficient and high speed overlap free Karatsuba based finite field multiplier for FPGA implementation. This cryptography systems has become an indispensable component of nearly every communications equipment. A polynomial multiplication is recognized as the slowest and most area consuming process in ACC systems. This paper presents a unique hardware design for efficient FPGA implementations of finite field multipliers for ACC systems. Okay, this proposed approach for modifying the high-speed overlap-free Karatsuba multiplier at a 2-bit design flow graph of hardware implementations with a 4-bit output method. This presents the 2-bit design flow graph approach has only 3-bit output method, which does not guarantee a valid output at a high precision bit. This research also reported the overlap and non-overlap designs of 4-bit and 8-bit and 16-bit design flow graph of Karatsuba multiplier, employing the proposed modified 2-bit design flow graph. Okay. Finally, we compared all the parameters in terms of area, power, delay at 4-bit, 8-bit, 16-bit and 32-bit size. Okay. Now we can verify the base paper. This base paper is fully designed for the Karatsuba based finite field multiplier with two techniques, overlap and non-overlap method. Okay, so here they are given two different architectures. One is a non-overlap method and another one is a overlap free Karatsuba multiplier. Okay, so both the architectures it will be same in the 2-bit KA method. Okay, so Karatsuba multiplier. Okay, so that 2-bit architecture they are given in here. Okay, figure 2A. Okay, so here what is the difference means in the normal multiplications 2 into 2-bit multiplication will get a 4-bit output, but in this cases they are taken only 3-bit output as per the architecture. Okay, so this 3-bit output it will affect in the high precision value. Okay, we will show the examples in the simulation. Okay, so this is the existing part of the simulation. Okay, so here this is a data check value. Okay, so here we are given a data A equal to 3 and data B equal to 3. So 3 into 3 equal to output is 9. Okay, this is a normal value. Okay, but the Karatsuba value is 5. Okay, why? Because the output of C0 equal to 1 and C1 equal to 0 and C2 equal to 1. Okay, but the C3 will not present. Okay, so that is a problem we are handling in this circuit. As per this architecture, a 3-bit design C0, C1, C2 will create a mistakes in the 4-bit architecture, also 8-bit architecture, also 16-bit architecture. Okay, so it will affect it as a high precision method. Okay, so we have created a new architecture, so with a 4-bit work. Okay, so we will show that architecture in the document. So this is the existing architecture and this is the proposed architecture. So the proposed architectures we are taken as a 4-bit output C0, C1, C2, C3. Okay, so additionally 3 logic gate we are added in the architecture. Okay, so based upon this architecture the 2-bit design will provide the output both 3 into 3 equal to 9. Okay, so this is a simulation for 2-bit Karatsuba multiplications. Okay, so based upon this 2-bit we are created other architecture design with a non-overlap and overlap method with a 4-bit, 8-bit and 16-bit architecture. Okay, so now we can verify the coding part. So this is the existing method of the coding. We have developed a overlap free method as per the figure 3 architecture. Okay, so here you can verify this is a test bench of the architecture. So here we are developed up to 16-bit. Okay, so here 16-bit size we are given input on here. Okay, for verification purpose we are used as a data check and error values. Okay, and this is a input method. Okay, we are generated on here. Okay, and this is a top model architecture. So this 16-bit architecture we are used with the 8-bit architecture of multiplier. Okay, so here 8-bit overflow multiplier, 8-bit overflow multiplier and 3 multipliers we are used as per the same architecture. Here 2-bit they are used, right? The same method we are used as a 8-bit method. Okay, so based upon that architecture we are developed it, and this is a as per the overlap free circuit we are developed a coding part on here. Okay, and these are the 8-bit, 4-bit and 2-bit coding. Okay, so here we can show the synthesis report for this work. Okay, so here it will be take slice LUT 174, occupied slices equal to 94, and IOB is equal to 63, and delay you can check it on here. Okay, delay it will take 7.128 nanoseconds. Okay, and you can check the RTL schematic. This is a KM Mult 16-bit overlap free architecture. Okay, so here you can check the 16-bit architecture. So here we are used as a 3 8-bit architecture. Okay, so this 3 8-bit architecture internally it will have a 4-bit overlap free method. Okay, so this is also the same method. Okay, 3 4-bit multiplier we are used. Okay, inside of the 4-bit multiplication part we are used as a 3 2-bit multiplication, 1 2 3 2-bit multiplication. So this is a 2-bit architecture diagram. Okay, so here K mul 2-bit equal to as per the design we are developed the code. Okay, so here it will be presented 2 XOR gate, 3 XOR gate, 3 AND gate. Okay, and now we can show the proposed method of the 16-bit. Okay, so this is a proposed method with a modified 4-bit architecture. So here you can check the slice registers equal to 197, occupied slices 102, IOB is equal to 64, and synthesis report you can check delay. Okay, delay equal to 7.311 nanoseconds. Okay, and you can check the RTL schematic on here. Okay, it will be same, but the overlap circuit and the 2-bit architecture it will be different. Okay, so as per the 2-bit architecture of 4-bit output, so we are remodified the overlap architecture for every bit size. Okay, that means the 4-bit overlap circuit we are remodified it. Okay, as per the 2-bit, and 8-bit also modified, and 16-bit also modified. Okay, so here this is a 2-bit method. Okay, so here the same 3 input AND gate, 2 XOR gate, and 1 AND gate, but here the architecture will take as a inverter logic on here. Okay, so here we are chosen as a inverter method, right? So based upon the inverter method it will be created this kind of RTL. Okay, so this is a proposed 4-bit method. So here you can check the 2-bit architecture of 4-bit output. Here you can check C0, C1, C2, C3. Okay, all the bit we are taken. Okay, it will be presented. This is a 16-bit simulation. Okay, existing method. Okay, so here you can check the 16-bit simulation architecture. Okay, you can check the data check value and data KA value. So it will be same. Okay, it's not showing any error. Okay, so up to the highest value also 32768 and 32, the output will take a same value only. Okay, so we are given a more number of values here. Okay, here you can check the B equal to 16384. Okay, and here you can check A equal to 32768 and B equal to 8192. Okay, the output will be present will be same. Okay, so it will be working properly with 0 errors. Okay, and so this is a proposed method simulation process. As per the Xilinx report, we are updated the comparisons document. So here we are updated the comparison document 2-bit, 4-bit, 8-bit and 16-bit. So we are developed all the codes, but we can't possible to show all the codes in the video file. Okay, so here you can check the folders: 2-bit, 4-bit, 4-bit overlap, 8-bit, 8-bit overlap, 16-bit, 16-bit overlap, and proposed method. Okay, 2-bit, 4-bit and 8-bit, 16-bit, all the things we are developed it. Okay, and all the comparisons we are updated in the document. Okay, so this is a 2-bit, 4-bit, 8-bit, 16-bit existing proposed. This is a method for overlap free method. Okay, and this is a comparison analysis chart, and this is a comparisons of Karatsuba multiplier overlap method. The same method we are developed in 2-bit, 4-bit, 8-bit, 16-bit with existing and proposed architecture, and this is a comparisons analysis chart. Okay, As per this project existing and proposed, we have written an abstract document for this project. Okay, so this is a title and base paper abstract enhancement of this project. Okay, here enhancement to remodify the 2-bit DFG hardware implementations of Karatsuba multiplier with a 4-bit output method, to develop the overlap and non-overlap design 4-bit, 8-bit and 16-bit DFG Karatsuba multiplier using proposed 2-bit DFG Karatsuba multiplier, and compare all the parameters to the existing 4-bit, 8-bit, 16-bit KA multiplier. Okay, and proposed title and proposed abstract, existing system, okay, existing architecture, disadvantages, proposed system and proposed architectures, okay, and related notes we are given for your verification. Okay, and finally literature survey references. Okay, thank you.
If you need more video related with VLSI projects implementation, please like and subscribe this channel.